Hello, I'm Mrs. Edwards, and today we're going to go over the mean value theorem. I've written out the mean value theorem here for you. If f is continuous on the closed interval a to b and differentiable on the open interval a to b, then there exists some x that we're going to call c on the open interval a to b such that the derivative of f at c is equal to f of b minus f of a all over b minus a. Well, let's go ahead and break this theorem down a bit. So what we have in the beginning is f is a continuous function on the closed interval a to b. Surprise, surprise, since every theorem that we've encountered so far begins with the function being continuous on a closed interval a to b. So that means we're starting off our function at a with a closed dot. We're finishing this function at b with a closed dot, and then we're going to connect point A to point B here without lifting our pencil. Now, we could do that in a number of ways. I just randomly connected A to B. Okay, if we continue reading, it says, and differentiable on the open interval A to B. Now, the reason it can't be differentiable on the closed interval is because differentiable means you can find the slope of the tangent line, and you cannot find the slope of the tangent line at an endpoint, right? It's going to teeter there, so the derivative never exists at an endpoint. So we have two prerequisites: that the function is continuous, don't pick up your pencil, on the closed interval a to b, and differentiable so you can find the slope of the tangent on the open interval a to b. That also means we can't have a cusp. If we had a cusp in there, then we would have a point where this function was not differentiable. So this curve is also going to be smooth as we connect it from a to b. Next, it says there exists some x equals c on the open interval a to b. Okay, x equals c on open interval a to b. That means that there's some x somewhere between a and b on the x-axis that we're going to call c. Now, maybe it's right there. But right now, I don't know where it is. All I know is it's between a and b. So I'm going to take that off temporarily. And then we're going to continue on. It says such that f prime of c equals f of b minus f of a over b minus a. Well, this statement is to help you figure out the location of that x equals c between a and b. All right, so let's break this part down a little bit. What does f of b minus f of a over b minus a mean? Well, here we have those endpoints, right? So if we have those endpoints, if we were to substitute a into this function, we would get out f of a. So this point right there is a comma f of a. And if I substitute b into the function f, I would get the coordinate b comma f of b. Well, y coordinate minus y coordinate over x minus x, oh my goodness, there is slope. Okay, the notation maybe looks a little funny to you. All right, so instead of y2 minus y1 over x2 minus x1, we have f of b minus f of a over b minus a, which just represents the slope between those endpoints. All right, so we have slope between the endpoints. And then f prime of c, let's focus on that part, f prime of c. Well, let's say c was there. F prime of c means we go up there and we find the slope of the tangent to the function, right? The derivative means slope of the tangent. Now you can see in this picture right now, the slope of this green line is not the slope of the red line. But in general, f prime of c means the slope of the tangent to the curve. So somewhere between this endpoint and this endpoint, the slope of this green line is going to be the slope of the red line. That is what the mean value theorem is guaranteeing. Slope of the tangent at x equals c. All right, so if these two things are equal to each other, You know, when two lines have equivalent slopes, then those lines are parallel. So I'm going to draw in a line parallel to this slope between the endpoints, and we're just going to keep on moving it until we're tangent to the function. So right there, see how right there we're going to call that C, the slope of the tangent at x equals c is equal to the slope between the endpoints. Another way that you can describe the slope of a tangent line is the instantaneous rate of change at that point C, right? Slope of the tangent lines and instantaneous rate of change. How fast something's going at exactly that one moment in time. And then slope between the endpoints, that is really like a slope of a secant line. And so that ends up being the average rate of change. So the meaning behind the mean value theorem is we know that there's going to be some time, some c between A and B where the instantaneous rate of change is equal to the average rate of change. Let's do one example where we're finding that c value where the derivative is equal to the slope between the endpoints. Before I really get started, I'm going to go ahead and rewrite this function as x minus 2 to the 1/2, because as a calculus student, I do not like this square root symbol. I prefer this notation. Okay, so focusing on the given information, we're on a closed interval from 2 to 6. So we're starting with a solid dot, we're ending with a solid dot. We can also see that this function is continuous and differentiable between 2 and 6. All right, so no cusps, no breaks, no asymptotes. Okay, it's differentiable and continuous. We don't pick up our pencil. Okay, next, we're trying to find that c value. So ultimately, we need to find the derivative and set it equal to the slope between the endpoints. Looking at our function f of x, to find the derivative, we're going to need the power rule and the chain rule. So 1/2 moves to the front. So we have 1/2 x minus 2, subtract 1 off the exponent. So 1/2 minus 1 is to the negative 1/2. Chain on, multiply by the derivative of x minus 2, and that's just 1. So the derivative function is 1/2 x minus 2 to the power of negative 1/2, technically times 1 on the end. Right, then I'm going to rewrite that to get rid of the negative exponent. So x minus 2 to the 1/2 is in the denominator. I just use the root because I'm done taking the derivative. Now I've found the derivative and I want to set it equal to the slope between the endpoints. So here's f of 6 minus f of 2 over 6 minus 2. In other words, I have a coordinate here and a coordinate here, and I'm subtracting the y's over subtracting the x's. We end up getting 1/2. Graphically, what that means is 1/2 is the slope between the endpoints. Now, there is some x value out there where the derivative is equal to the slope between the endpoints. Kind of going above and beyond here, I don't think it's completely necessary, but since I'm looking for an x that we call c between 2 and 6, I went ahead and just rewrote the equation and replaced the x with c. Okay, that's maybe a little too far, but nonetheless, that's what I did. All right, so we need to solve this equation, and we will know the x value between 2 and 6 that this happens. All right, so to solve this equation, there's a couple ways you could do it. You could multiply both sides by both 2 and the square root of c minus 2, because you multiply by the denominators, and all those denominators go away. Or if you see that you have only one fraction equal to one fraction, you could just set the diagonals equal to each other. In other words, 1 multiplied by 2 is equal to 1 times 2 root c minus 2. All right, so there we have it. Starting to get c alone, I'm undoing the order of operations. So I'm going to get rid of multiply by 2 by divide by 2. This square root is really to the 1/2, right? It's exponents. So to get rid of those exponents, to get rid of square root, I'll square both sides. Now we've freed up what's inside that root. So I add over 2 and I have c equals 3. So we have just found the x value that we're calling c between 2 and 6, where the slope of the tangent is equal to the slope between the endpoints. Let's look at that in the picture. Here's 3, and then if I plot that point, notice the slope at x equals 3, the slope of the tangent right there is the same as the slope between the endpoints. Here's a scenario to help you remember the mean value theorem. I'm going to just start off laying out that scenario, and then we're going to see how the mean value theorem applies. So we have this driver, and he is going very fast, but he is not hoping for a speeding ticket. So he's been on the lookout for police officers, and he's speeding, but in the far distance, he sees a police officer. And he's like, oh, I'm good, I see you. So he slows down, and that first police officer clocks him, and he's clocked at a speed that is within reason. Then he gets a ways past this police officer, and then he starts speeding again, crazy speeding, but sees another police officer in the distance. Same thing, sees him, slows down, and then continues on his way thinking, I am in the clear. The first police officer in this scenario clocked him at 55 miles an hour. The second police officer clocked him at 50 miles per hour. But we know that this car was speeding because the distance between these checkpoints is 5 miles. And it took the driver exactly 4 minutes, which is 1/15 of an hour, to go from checkpoint 1 to checkpoint 2. And if we know the time it took to travel a distance, we can find average rate of change, the average speed this driver was going. So at time 0, we were at 0 miles. At time 1/15 of an hour, we were at 5 miles. Subtracting the y's over subtracting the x's, the average rate of change, the slope between the endpoints, is 75 miles per hour. So the mean value theorem guarantees that there is some time between time 0 and time 1/15 of an hour that the car was going exactly 75 miles per hour. May have been going more than that at some point in time, but the mean value theorem is guaranteeing that since the average rate of change from 0 to 4 minutes is 75 miles an hour, that at some time instantaneous rate of change must be 75 miles an hour. So that police officer could give them a ticket for going at least 75 miles per hour. Now, in this scenario, I'm giving it to you, the police officer is so in the right, but darn it, doesn't that just feel mean? The mean value theorem. So mean value theorem sets slope between two endpoints equal to the derivative